All right, we'll go ahead and get going. Thank you again, everyone, for joining this morning. Please note that you will be muted throughout the duration of this presentation. Please enter any questions you have into the chat, and after Ben's presentation, we will address those questions at that point. And I will turn it over to Ben to get us started.
Thank you, Ryan. Good morning, everyone. I appreciate you coming here today for the talk. My name is Ben Segrin. I'm a researcher at the National Renewable Energy Lab, and I'm joined virtually by my co-authors Ashok Sekar and Emma Tomei. So in this webinar, we'll present some recently published research studying solar adoption by low and moderate income households in the U.S. Increasing the adoption of solar among these households remains an important goal because of its promise to simultaneously both reduce energy burden and support the just distribution of renewable energy. However, scaling low-income solar programs remains challenging due to affordability and access issues by the target population. Most existing low-income solar programs have occurred under publicly funded programs, highlighting the importance of increasing the cost effectiveness of these programs if scaled to larger volumes. To study these issues, we developed a new household level data set studying solar lead acquisition, referrals, and adoption to ultimately understand the processes through which these households have adopted solar in California. And from this data set, then we developed machine learning models to predict two sub-mechanisms in the adoption process. First, whether an otherwise qualified lead becomes quote-unquote lost or non-responsive to outreach efforts. And then for existing clients that do go solar, whether they refer solar to their peers or not. One important caveat I want to let you know about this data set is that for the program analyzed, participants received their solar system at no cost. So this de-emphasizes some of the typical economic drivers of solar adoption that you might see in other studies. So we'll show that both lost leads and referrals can be well predicted using machine learning. We'll demonstrate the variables that improve the prediction and their degree of influence, as well as provide implication for new program design. I think our main finding, though, is that referrals are both the highest quality and largest source of low-income solar leads, and this to us provides a promising mechanism to expand solar further. So this article is actually one of 5 studies funded by the U.S. Department of Energy Solar Energy Technology Office. Our first study on the left studied technical potential of rooftop solar among low and moderate income households. And you can access those results via the link here or going to our website. This study, which we're talking about today, uses historic data to understand drivers of adoption referrals. And then other studies have surveyed solar adopters. We've done comparative city case studies to understand neighborhood level factors, and then also done some experimental work to test what factors actually increase referrals and adoption. So again, for more information, please check out our website, NREL Seeds. I think you can search for it fairly easily. I think that it's worth also pausing to ask why solar adoption in underserved communities is so important. And though it's been increasing recently, it's still a contentious issue. So I think from an equity point of view, residential solar has been disproportionately adopted by high-income households who often are benefiting from publicly funded incentives. So because of this, there's a growing backlash against solar policies that appear to favor the more affluent members of society. So I think without correction, rooftop solar risks becoming the purview of the wealthy. It risks reputational backlash, and that ultimately its deployment is not seen as being part of the public best interest. Second, maybe from a more market point of view, rooftop solar in low and moderate income communities represents simply an enormous market opportunity, one that is just largely underdeveloped. So prior studies by NREL have shown that over 300 gigawatts of rooftop solar potential exists in these communities, and we're really leaving a lot on the table by not fully developing these markets. Moreover, equity in solar adoption can lead to many other cross-cutting policy objectives, things like reducing household energy burden and supporting energy equity and decarbonization goals that communities may have. So it probably goes without saying that some families face more barriers to adopting solar than others. I think this starts with the affordability question of rooftop solar is still quite capital intensive technology, and many households simply don't have cash on hand to purchase them. But many other barriers challenge widespread solar penetration. So starting with just the simple classic split incentive problem, a large fraction of low-income households live in multifamily or renter-occupied buildings, which, as we know, discourages adoption. Even among single-family households, multiple barriers remain, ranging from structural suitability for solar, ability to secure financing, inability to monetize tax-based incentives because of insufficient tax burden. There's also many behavioral barriers, including information asymmetry, the cost of searching for information, and distrust of outsiders or new programs. So this study specifically looks at just one of these quadrants, so the low-income owner-occupied potential, and many other work that needs to be done to study some of these other quadrants of renter-occupied. So as I mentioned earlier, existing low-income solar deployment has largely occurred via public programs. Probably most prominent of these are the set of programs that have been funded through the state of California, which include the SASH program and the Cap and Trade program. Historically, many of these programs have been operated by a third-party intermediary on the government's behalf, and this intermediary occupies a nonprofit role and is generally responsible for generating program leads, doing site assessment, and ultimately installing programs. Within California, Grid Alternatives, a nonprofit, has administered that state's program for over a decade, with nearly 11,000 single-family low-income systems deployed over the last decade. And again, as I mentioned earlier, in California, the state program currently subsidizes the entire system cost. So in this study, we partnered with Grid Alternatives, receiving an anonymized version of their program activities and their data. So this household level data is particularly valuable because, first of all, it's simply the single largest source of historic data on low-income solar adoption that's available. And so it really does represent sort of the best in class of what we can understand about these programs. Second, because of its unique and sole provider of California's low-income solar programs, this means that the data from their database captures all solar leads and referrals, so that's sort of a self-enclosed system. Before moving on to more of the results, I think it's also important to pause on why we care about referrals in the first place. So if you're not aware, first of all, referrals are currently the lowest cost method of generating new solar clients. They are valuable enough that referrers are often paid several $100s by an installer per successful install. Referrals currently constitute somewhere around 40 to 50% of all solar clients in the market rate solar industry. And in a recent study, almost all of the solar installers interviewed reported that they asked or incentivized clients to provide referrals. I think another interesting aspect of referrals is that, unlike traditional media advertisements, referrals as a lead source can't simply be manufactured, and thus they can be challenging to widely scale for volume or to scale into new geographies. One reason that referrals are so effective, though, in driving technology adoption is because they draw on what we call peer influence. So adopting new technologies is risky, with uncertain benefits and risks. Relying on the advice and experience of our peers helps to quote-unquote de-risk a technology. And so unsurprisingly, many studies have shown repeatedly that peer influence, both spatial peer influence, meaning the number of systems installed around me, and social peer influence, meaning whether my friends, families, and other acquaintances tell me about solar, both of those factors have been shown to increase adoption of solar. So a key insight here, though, is that many of these prior studies, while they have successfully shown that knowing the number of solar installations nearby or the number that were recently installed, meaning over time, can both predict solar adoption. But our question is, to what degree are these counts of nearby installs actually proxies for the underlying social relationship? That is, while pure effects surely drive solar adoption, to what degree are they a proxy for these underlying referral mechanism? Is it the referral itself that matters, or is it knowing just the counts of it? Okay, so moving on to some of our first results here. So after cleaning the data and organizing it, we first show program outcomes and how a lead flows through the system. So one kind of criteria here is to understand the eligibility criteria for participating in this. So several criteria that a client needs to own and live in their own home. Their income needs to be below 80% of the area median income. There are geographic eligibility criteria, such as living in a qualified census tract, and many other sort of policy goals here, disadvantaged communities, opportunity zones, and so on. Prospective clients follow a customer acquisition pipeline that's similar to that of market rate solar, diverging primarily to first determine their program eligibility rather than ability to pay for solar. So they start with a pre-screening process to determine their program eligibility, followed by submitting an application if they are deemed eligible. Next, the installer would complete an insight visit to evaluate technical suitability, develop a tentative system design, and then ultimately indicate approval for installation to proceed or not. So I think a few insights emerge from this analysis of the pipeline. So first, a large fraction of the leads that Grid Alternatives contacted did not go on to receive solar, over 85%. Of these, the two largest reasons were ineligibility to participate due to geographic ineligibility. So 30% of all leads with resolved status were excluded for that reason. And then second most, disinterest in solar, or just losing contact with the system, was about 17%. And then at the time of the analysis, around 20% of the leads in the system were still in the acquisition pipeline that had unresolved status, meaning pending or waitlisted, and were not analyzed in the study due to. So our next result is looking at the mechanisms through which LMI solar leads are generated. And so there are many mechanisms that we identified, and each with different levels of effectiveness. So these are referrals by existing clients or other individuals, community supporters, and organizations. Second, leads connecting through web search. Third, traditional printed advertisements on websites, newspapers, other types of advertisements. Also targeting ads by postal mailers and emails to potential participants. Also canvassing events, canvassing entire neighborhoods, doing door-to-door events, holding block party type solar installation events. So out of all of these channels, so around 30% of all leads were ultimately generated through referrals. So referrals constitute both the largest source of leads, and as you'll see later, also one of the largest source of leads and the largest source of installations. Other channels that were successful, however, include web search, digital and print advertisement, and so on. About 25% of the leads in the system simply didn't have a recorded lead source. So referrals were the largest source of leads and clients, and they were also one of the most efficient sources of leads, where 20% of all referrals ultimately led to an install. This wasn't the highest, but it was nearly one of the highest conversion rates. Okay, so using this data, we developed predictive models, or what you might call machine learning models, to study three questions. First, where are installations happening? Can we predict them just using tract level data? Second, can we predict whether an otherwise qualified lead will become lost or disinterested? And then finally, can we predict whether a former client will actually provide a referral? The study is ultimately grounded in two practical motivations. So first, what can we learn from this historic program to inform expanded deployment in other geographies, new types of programs, or programs in different states altogether? And then second, can predictive models actually be practically used to inform program operations? And we'll touch on that a little bit later, but how accurate do the models need to be to provide value to the practitioner? And then what are some of the equity implications of using machine learning models for prediction? So one of the points of comparison that we also wanted to understand in the study was what type of data is actually needed for successful prediction. So for example, how successful would prediction be using only public data? So for example, if we have public data, for example, characteristics of the census tract that a household lives in, is that sufficient to predict whether they'll become a lost leader or provide a referral? Contrast, is it necessary though to have personal data about the household, which in addition to being intrusive, it might be difficult to collect individual level data for initiating new programs. So our household level data is developed from a combination of several proprietary and public data sets. And you can see some of these here. The core data set, as I mentioned earlier, is a customer relationship management database comprising all leads, clients, and systems installs that Grid Alternatives interacted with from 2009 to 2018. This data set allows us to construct both the date of creation of a lead and their source, as well as their outcomes, like whether they installed or not. For leads that ultimately generate to clients and provide referrals, the database provides rich details about the referral, such as the date, the location of both the referrer and referee, and other elements of their dyad. And so based on some of this data, we can engineer additional features like what tract they live in. From the tract, what were the average socio-demographic factors for the tract? What are some environmental indicators for that community, as well as proximity to other solar installations, proximity both in terms of distance and in time. So again, as I mentioned earlier, we also partition the data between both public data sets and private data sets. Our modeling approach employs several data science best practices for developing predictive models. So first, our data set is randomly split between a training/validation set, which comprises 80% of the data points, and the rest, 20%, is withheld from the model for testing. So sort of following the classic approach, first we fit the model on this subset of the data, the training data set. And then next we have to validate the training model to evaluate what are called hyperparameters. So there are many knobs and dials that one can evaluate within a machine learning model. We don't know what combination of quote unquote hyperparameters will provide the best fit. So that's why we have to validate the training fitting. We can also use a technique called cross-folding, which I don't have a good graphic for it here, but it essentially looks at different subsamples within the data, withholding different parts of it to better utilize the data that's available. Then finally, once we've trained the model, we can evaluate it on the test data set. So again, evaluating the model fit on out-of-sample data that was not used for the training. This allows us to understand whether the model was overfit or not. And then finally, we can analyze the results. So predictive models can be evaluated in many ways, but ultimately what we care about the most are how well does the model predict out of sample, meaning is it overfit or not? And then does the performance of the test data set approximate that of the training? Because if you have dramatically different results for the training set versus the test, then that's also an indication of that the model is overfit and unlikely to produce useful outcomes. There are many specific metrics that one can use to assess performance. We ultimately use a metric called balanced accuracy, which is useful for data sets that are imbalanced, meaning in our particular data set, we have many more clients that did not provide referrals than those that did. So we need to balance the data set so it doesn't overfit on predicting, say, negative referrals. So again, kind of overview here of some of the current techniques that one can use. There are many types of what are called tree-based models. So the most simplest one is what you would call a simple decision tree that partitions features according to the outcome of interest. So you can see here this actually figure doesn't correspond to our data set, but you might partition data set based on someone's income, and then first based on their home value, and then based on another factor. And so as you move down the tree, it branches out, and you're sort of clustering the outcomes there and trying to find the optimal partitioning of the data. Next, though, a random forest model, which is very popular these days. is a more enhanced version of a decision tree. Random forests are more complex because it operates by developing a decision tree that specifically identifies the optimal splitting points for each feature. And random forests actually train multiple decision trees based on a random subset of the data, averaging their predictions to yield a less biased model. One of the really nice things about random forest models as compared to, say, your classic ordinary least squared regression model is we don't actually have to specify the model in the sense that it will natively incorporate nonlinear and interactive variable effects, again, without explicitly specifying the interactive effects, say, between income and home. Though one really key thing here is that we do lose a certain amount of interpretability about the results. Finally, and actually the model type that we used in the study, extreme gradient boosting is an even more specialized version of a random forest. So a gradient boosted random forest, sometimes going by the acronyms XGB, builds an ensemble of decision trees successively fit based on predicting the residuals or errors of the previous models. And this is towards the greater point of reducing overfitting. Finally, as a point of comparison between the XGB models, we also developed what are called naive Bayes models as a baseline to understand how much the XGB specification itself improved prediction relative to just a simpler model. So how much bang do you get for having a complex model versus just a very, very simple one? Okay, so moving on to our results, our key results here. So just want to start off with an example, kind of thought experiment about when are predictive models actually useful. So in theory, improving the prediction of lead conversion or predicting referrals could have substantial implication for practitioners and solar installers because it could lower their customer acquisition costs by providing more accurate assessment of a client's outcome. And this has both private and social benefits. So in this illustrative example, imagine a predictive model that predicts referrals with a sensitivity of 95%, meaning sensitivity is the percentage of true positives that are correctly identified, and a specificity of 90%. Specificity is the opposite, meaning the percentage of true negatives that are accurately predicted. And using our actual referral prevalence of 12%. So what that means is of all the clients, only 12% of them actually provide a referral. So in this null case, we could imagine a practitioner contacting 1,000 clients, seeking for these 1,000 clients to provide a referral. And then of those, we know that they might receive 120 actual successful referrals. That would be in the null case. If you use a predictive model, using the predictive model, the practitioner would infer that 202 clients might provide a referral and 798 might not. So of these 202 referrers, 114 are actual referrers, true positives, and 88 are not. So of the 798 inferred non-referrers, 792 would not provide a referral, meaning they're true negatives that were correctly identified, but 6 would have been predicted to, a false negative. So taken together, the practitioner would have required about 20% of their staff time, 202 clients contacted out of the 1,000 to acquire 95% of the actual referrals. But I think one of the equity implications here is that predictive models always imply that some households are not pursued. That's an inherent implication of using a predictive model. So used well, they can reduce time spent for a positive outcome, but this also has equity implications in the sense that our model could be biased and systematically excluding households that are not predicted by the model to provide referrals. So taken all together, these are some of our core results showing the predictive model's performance. So the orange lines show the prediction for the lost lead model, the blue for the referral model, and then these are along the x-axis looking at just the public data alone, just looking at the private data alone, and then looking at the combined public and private data. So I think that some of the core takeaways here for me are that the lost lead model using the XGB specification had about an 87% balanced accuracy. whereas the referral model had a 63% balanced accuracy. So we were able to predict lost leads more precisely than we were for referrals, and that both models substantially improved using private data, although there's this marginal impact of adding the public and private data together. We'll dig into these results a little bit more in the next slides. Just showing some of the other results here for the lost leads model performance. This shows the points that you saw in the previous figure, but in tabular format. So again, our preferred specification is the XGB model type using all of the data. It achieves a balanced accuracy of 87%, and you can see some of its other core metrics here: sensitivity, specificity, precision, and F1. And again, it does outperform the naive Bayes model, as well as using a smaller subset of the data. As noted earlier, despite potentially receiving a free solar system, over 20% of all qualified low-income leads were quote unquote lost due to a lack of interest or drop-off. So this suggests that improvements to the prediction of lead outcomes could potentially improve the solar program's operational costs. So for example, with improved performance, a practitioner could selectively focus resources on leads that are identified as having a high propensity of going solar, or you could put additional effort to convert potential lost leads to clients. You might also apply different marketing and outreach strategies to different population. So predictive models are traditionally understood as having little explanatory power, and this is especially true for random forest models. We are able to use an emerging method called the Shapley Additive Explanation Framework, or SHAP. SHAP is a game theoretic framework for explaining the outcomes of machine learning models, and it works by assigning an importance value to each prediction in the model. These importance values are shown here, and so what this shows is our feature importance plot, showing the most relevant features for the prediction ranked from most important, meaning most impactful for the prediction, as well as their magnitude. So for example, the most important feature for the lost lead model was simply the number of referrals within 1.5 miles. And that alone explained almost 20% of the overall prediction. Several other features, though, were important. You can see here, there's quite a few here, but you can see there are several other factors that we identify as proxies for peer effects. So several variables that talk about number of installations within 1 mile, within 1.5 miles, differentiating between both low-income solar installations and market rate solar installations, as well as installations occurring over, say, the last 6 months versus the last 12 months. So clearly here, several proxies for peer effects are important for predicting lost leads. And we also see importance for several environmental measures. Sort of on the lower half here, hazardous waste facilities within the tract, drinking water contamination, and so on. We can go even deeper, though, and not just understand which variables were important for prediction, but also their direction and degree of influence. So here we show these SHAP values converted into what's called a conditional dependence plot. So this shows just a subset of the 10 most important features within the lost lead model. Positive values on the y-axis indicate that lead was more likely, less likely to be lost, or more likely to be retained. And then x-axis shows the value of the variable itself. So walking through the figure on the top left cell, number of referrals within 1.5 miles, you can see that having no referrers within 1.5 miles leads to about a 10% increase in the probability that the lead was likely to be lost. But then as more referrers are located within 1.5 miles of the lead, that decreases the likelihood that they'll become lost, or conversely increases the likelihood that they'll be retained by the program. So for example, leads with 0 referrers within 1.5 miles were approximately 10% more likely to become lost, whereas having 5 referrers nearby decreased the probability by 50% relative to those leads that had 0 referrers nearby. For binary variables, for example, for binary variables such as region in the Bay Area, the interpretation is simply between these two outcomes. So for example, clients that reside in the Bay Area were 10% less likely to become lost relative to all those that didn't. Now, I do need to caveat that these figures don't make causal claims. We're not showing that there's a causal relationship between number of referrers and outcomes of lead loss. These are showing us correlations. So for example, they're showing that increases in the number of referrals was correlated with the decrease in the probability of lost lead. And this can get nuanced, but just to say we're not making any causal claims here. So synthesizing these two together, both the feature importance and conditional dependence plot, we can observe that peer effects were a significant contributor to the prediction. Nearly half of the top 10 variables were proxies for some types of peer effects. And there's also influence from both market rate and low-income installations. Next, 3 of the top 10 features were household level characteristics, things like income, household size, and racial composition. 2 were neighborhood level characteristics, as I mentioned earlier, whether the household lived in the Bay Area or whether they were served by the Pacific Gas and Electric utility. And though they're not shown here, there were several environmental variables in the top 25 overall, as I mentioned earlier. Next, moving on to our referral model. So, despite being one of the largest and highest propensity lead sources, only 12% of LMI solar adopters ultimately provided a referral. And so similar to the formula logic with the lost lead model, with increased prediction of refers, a practitioner might prioritize their marketing effort to those clients that are predicted to provide referral, or try to target future clients with a similar file. So as with the lost lead model, we're going to compare it against the data type and against the model specification. However, unlike the lost lead model, the referral model is somewhat less accurate. Its balanced accuracy was 63%. But it's still consistent with the lost lead model in the sense that the XGB specification and using all of the data led to the best type of prediction. Like the lost lead model, we can show the feature importance plot for the top 25 variables, as well as the collective influence of all the remaining variables in the model. So like the lost lead model, distance to nearby referrers was the most impactful variable. You can see many other variables here are important for prediction. Unlike the lost lead, monetary and financial influences are driving some of these predictions. So for example, whether or not the client provided or received a monetary incentive for providing a referral, as well as things like expected solar system production, expected solar bill savings. And also internet access was interesting here, was one of the most important variables, whether or not internet was available in the household. So again, looking at the conditional dependence plot for the referral model, here, like the lost lead, positive y-axis values, CHAP values, indicate that the client was more likely to provide a referral. And again, just like the lost lead model, our most important variable is distance to the nearest referrer, where being further away from referrers made someone less likely to provide a referral. Sorry, not made, but it was correlated with lower probability of referral. So kind of in an intuitive sense here that being nearby to other referrers increases the probability that a client would provide a referral themselves. So interestingly, knowing the number of existing solar installations nearby was not of substantial value in providing referrals, unlike the lost lead model. Just really distance to other referrers themselves. Also, as I mentioned earlier, economic factors had a strong influence on the referral model. Also, unlike the lost lead model, environmental variables were not hugely significant in predicting them. They show up, but not hugely significant. So aside from traffic density, there are no other environmental related variables that we observed in the top 25. You know, synthesizing these two together, two variables that were common to both the loss lead and referral models were, again, counts or distance to nearby referrers and household size. All right, so closing this out a little bit, what are some of our conclusions and implications? So first, these models could help support affordable solar program uptake and help us understand the possible policy outcomes. So applying these models in practice could provide substantial savings in terms of staff time to acquire leads and also acquire referrers. And I would refer you to the paper for more of the mathematical detail of how we're coming up with 20% and 56%. So we do think that predictive models can be of importance in helping to reduce operational costs and scaling these types of programs to new geographies. So clearly, one of our implications here is that referral incentives should be built into program design. So several mechanisms were important for acquiring leads for the programs, but none more effective than peer referrals. So not only were referrals the single largest source of leads, but they were also one of the most effective in terms of conversion rates. In addition, as we just showed, distance to nearby referrers was the most important variable in increasing predictive performance for both the loss lead and referral models. So again, we encourage practitioners to incorporate these mechanisms into future programs, for example, as a means of seeding new participants, so randomly assigning participants in underserved geographies, and also scaling them, leading to faster growth rate. Our second program implication is that more flexible eligibility requirements could potentially extend solar to more communities and potentially reduce administrative burden. So, despite this near total cost subsidization, acquiring clients for these programs remains challenging, where less than 15% of solar leads ultimately went on to receive solar. A large fraction of these leads were disqualified for this sort of intricate combination of geography, ownership, and income eligibility criteria. Though these criteria are certainly important for ensuring that these program funds are reaching the desired population, I would posit that they also impose additional administrative burden. So potentially loosening these requirements or simplifying eligibility criteria could make it easier to determine the eligibility and therefore so in conclusion, I want to wrap up with saying that a substantial concern of machine learning is the possibility of model bias to the detriment of communities or outcomes or households underrepresented in the data used to train these models. Though we suggest that low-income program operation costs could be reduced through using these data-driven models, clearly practitioners should proceed cautiously. So for example, to the extent that there are differences in program outcomes, predictive models could preference one sociodemographic group over another, thereby leading to inequitable program participation. So we have to balance both concerns. Thank you for your time. I've listed several points of contact here for both myself and Ashok. Please visit our project website. Please read our journal article and also subscribe to NREL newsletters. Thank you, and happy to take any questions at this time. I'll also, maybe while we're waiting for some questions to come in, introduce my colleague Ashok Sekar. Ashok, if you're able to join on here, maybe if you want to say a few words about what some of the takeaways were for you for this study. Ryan, I'm not sure if folks are able to unmute themselves at this point. Kai asks, will the slides be shared? Yes, they definitely will be shared. We will be posting these slides as well as a recording of the webinar to our website. We'll also be providing a transcript of the presentation. So that will take us, I think, a couple days to put up, maybe a little bit longer because of the holiday season, but it'll be up shortly. Okay, Don asks, what kind of referral incentive is best? That is a great question. I would say it's a question unexplored by this study, Don. So in this study, so about half of the participants were not compensated for providing referral, mostly in the first half of the program operation, and then about halfway through, Grid Alternatives decided to start issuing a referral incentive. I believe around $200. Please don't quote me on that. So just a flat $200 per successful referral that led to an install. But we do have another paper coming out. It's not published as of yet, but it does look at exactly this factor of design of incentives and how you can best predict. Sorry, not predict, but best encourage referral generation. Okay. Some more questions coming in the chat window. So Kai makes a note that there are issues with incentives. So for example, many cannot monetize the investment tax credit, and finance partners might consider the projects too small to fund. Yeah, that's definitely a barrier to low-income solar scaling. In this particular program, technically all of these systems were technically leased and not host-owned, and I think that was one of the funding mechanisms that Grid Alternatives decided to employ to get around the monetization issue. But yeah, certainly an issue, and I think that this is leading into a broader topic of sort of the investment tax credit provides a lot of benefits, but also provides a lot of complexity too. And if you don't have enough taxable burden, this is, for example, one of the reasons why the direct pay program could potentially increase deployment within these communities. Julie writes, we did the study with Grid Alternatives. Do you have information on how Grid Alternatives is using the information or adopting new practices? Yes, I mean, more anecdotal. So we did partner with Grid Alternatives throughout this program, both on this study here, as well as the other 5 that I had noted at the top of the talk. So our research team met frequently with Grid Alternatives, and tried to convey what we were learning, what we were seeing in the data, and vice versa. They always provided very useful, grounded feedback on what their interpretation of the data was. So I think there was a lot of back and forth there. I would defer you to Grid Alternatives specifically on how they've changed their operational practices. Sarah writes, what implications might there be for the dependence on the close proximity of referrals and ultimately installations and the local feeder's ability to support a maximum number of distributed solar systems before the distribution system infrastructure upgrades are needed? That is a really great point. I think maybe synthesizing it, that if you have too much proximity of DERs adopted within a very concentrated area, that could exceed the local capacity to support them. So that's certainly a concern. I think that I think that's a correlating factor for sure. If you have a high concentration of solar on one distribution feeder, then potentially that feeder would need to be upgraded, and that sort of has a negative directional influence. I would also say though that we in all of the analysis that we did, we didn't necessarily find that it needed to be extremely close spatial proximity. So it didn't need to be, I don't know, within 100 feet or on your block. So for example, the most predictive variable for the loss lead model was within 1.5 miles radius. So I think the size and extent of distribution feeders can vary, but my guess is that 1.5 miles radius, especially within a city, would comprise several distribution feeders. So that might be a mitigating factor, and spread out the adoption over multiple feeders. But certainly this is just a persistent issue that we tend to see solar adoption, both low income and market rate, spatially concentrated because of this key influence from spatial peer effects. Right. For these great questions, everyone. I appreciate it. Let's just pause a few more seconds here if there's any other questions that come in. Thanks, Kai, for joining.
Hey
Um,
Ben, sorry, this is Ashok Shekhar.
yeah,
Sorry, I was not able to join earlier. I had some issues with my mic, but I think you covered all the main points from the paper, from from the major results, along with the caveats and the implications for how for a practitioner. So kudos. I don't have anything to add actually,
okay,
but I just want to tell the participants, feel free to contact us, contact me as well in case you have any other questions regarding the study.
great. Thank you, Ashok. Appreciate that. Yeah, I'll just use that as a chance to close this out. So thank you, everyone, for coming and participating. We will be sharing the slides and as I said, a recording. Please do reach out to us if you have questions or further with you. And if not, I wish you all okay. Thank you.